Pre-Calc Honors students, Mrs. Myers here with your last and final lesson of Chapter 7. So this is Section 8, Day 2, and we are doing some more applications of determinants. So there are two things that we are going to use them for, extremely closely related. Okay, first is we're going to use determinants to find the area of a triangle. Now, of course, you know how to do this already using other methods, but this is just one more method that you can use for this kind of a topic. So anyway, if I give you the following vertices, all right, so we get 1, 0, 2, 2, and 4, 3. Okay, and I ask you to find the area of the triangle with those vertices. The way you use it with determinants, okay, is that the area is equal to plus or minus 1/2 times the determinant value of the matrix that is created by using the 3 points x1, y1, x2, y2, x3, y3 as columns 1 and 2, and column 3 is just 1, 1, 1. Okay, so the idea here about the positive negative is that an area of a triangle is only going to be positive, but yet a determinant value could be positive or negative. So it's up to you to just kind of see which, is needed based on the problem. So anyway, for our specific example here, we are going to say that the area is equal to plus or minus 1/2 times the determinant of the matrix 1, 0, 1, 2, 2, 1, 4, 3, 1. Okay, so we're not going to do this by hand, okay? Not for these problems right now. We would just go right to the graphing calculator. So I've already taken the liberty of doing that, and that determinant value is a -3. And then you just decide whether it's positive 1/2 or negative 1/2, and clearly it's the negative 1/2 that's needed here to get this area, which is then going to be 3/2, and that would be square units. All right, so if you just actually take the time to put this on a coordinate plane and you think back to what you learned in geometry, you could, of course, find the area of the triangle using one of those methods and compare and see that you get the exact same answer. All right, so second thing that we're going to do is we're going to use determinants to determine collinearity. Okay, so collinearity, if you don't remember, being that points all lie on the same line. Okay, so if I give you a set of points and I say, 0, 1, 2, 2, and 4, 3, okay, and I ask you, are these points all collinear? Okay, so we would do the following. Okay, we're going to take the determinant value of the matrix found by, well, same thing as before. Okay, x1, y1, 1 is row 1, x2, y2, 1 is row 2, x3, y3, 1 as row 3, and we're going to find out what this determinant value is, and if it equals 0, then the points are collinear. Okay, but if it does not equal 0, then the points are not collinear. Okay, now that actually would relate very, very closely to what we just did if you think about it, because what would the area of a triangle be if the points were collinear? Well, if the points are collinear, you wouldn't be forming a triangle, and hence you wouldn't be getting any kind of an area, and the area would be 0. So therefore, again, if you get 0 as this determinant value, which would mean that there'd be no triangle that would be formed, then the points are collinear. And if you do not get a determinant value of 0, get any other value like this, it means there would be a triangle's area that would be found, and therefore the points would not be collinear. Okay, so for this particular problem, okay, you would go 0, 1, 1, 2, 2, 1, 4, 3, 1. That determinant value is equal to 0. So these points are collinear. And really, you could just put them on one set of axes, and you could just see, of course, that there's a constant slope between them, so that would prove collinearity as well. So it's not like you don't know how to do this already, you're just seeing a different method for it. But what if I give you the points -2, -2, okay, 1, 1, and 7, 5? Okay, so are these points collinear? So you would set up the matrix -2, -2, 1, 1, 1, 1, 7, 5, 1. All right, and it turns out that determinant value is 6, so then these points are not collinear. Okay, so that's fairly straightforward. All right, so really those are just the two rules that we're learning, but now we're just going to do one more problem that's a little bit more involved, and it will review how we find determinants from what we did in the previous lesson. So what if I say to you, find x such that the points are collinear? Okay, and I give you 3, -1, 0, -3, and x, comma 5. All right, so I mean, obviously, if you were to get yourself a coordinate plane here, just make a little sketch. Okay, so 3, -1, 0, -3. Right, we see these 2 points right here so far. Okay, we can see the line that's determined by them. So what, comma 5? So 1, 2, 3, 4, 5. All right, obviously we can see that we're way over here with some positive x. I mean, again, we could just do slope and we would be able to determine that x coordinate, but I want us to use this whole idea of the determinant value for matrix. Okay, so we are looking for the determinant of the matrix 3, -1, 1, 0, -3, 1, x, 5, 1. Okay, we want that to be equal to 0 in order for the points to be collinear. Okay, so remember what we need to do to get a determinant value of a 3 by 3 matrix, okay, is you need to find first your minor values, then you apply your cofactor sign change to that, and then you take any row or any column of all those values that you just found and multiply it by the corresponding row or column values from the original matrix, and then add all those products together, and that gives you your determinant value, which we want to be 0. So really what we're just looking to do is we're looking to get a row or column of minor values that we know will include the x value at least one time. Okay, so in this case, since we put it in row 3, for example, if we use the minor values from row 2, we're going to be good to go. All right, so let's find minor values 2, 1, 2, 2, and 2, 3. Okay, so how this works again, if you don't remember from before, okay, is you are getting a 2 by 2 matrix that you can easily find the determinant value for by eliminating the row and the column that you have stated right here for the minor value. So minor value 2, 1 means eliminate the values from row 2 and column 1. What are you left with? You're left with -1, 1, 5, 1. Okay, and what is that minor value? So that's just the product of -1 and 1 minus the product of 5 and 1, which is basically -1 minus 5 or -6. Okay, so minor value 2, 2 says eliminate row 2 and column 2. Okay, row 2 and column 2 leaves you with 3, 1, x, 1. See how we're left with an x? Okay, and then that minor value is 3 times 1 minus x times 1, which is 3 minus x. And then minor value 2, 3, so eliminate row 2 and column 3, and we're left with 3, -1, x, 5. Okay, so that minor value is 3 times 5 minus x times -1. In other words, it's 15 plus x. Okay, now for row 2, okay, what are our cofactor sign changes? So here, remember our cofactor sign changes are positive, negative, positive for row 1, negative, positive, negative for row 2, and positive, negative, positive for row 3. Now that doesn't mean make it positive or make it negative. Again, the positive basically means keep the value, and the negative means negate the value. Okay, it's like multiplying it by a positive, multiplying it by a negative, essentially. Okay, so keep the sign, change the sign. So we apply our cofactor sign changes. So this -6 becomes a positive 6. Okay, this 3 minus x stays 3 minus x. Okay, and then this 15 plus x becomes -15 minus x. Okay, so since this is row 2, we're going going to take a look up here at row 2, okay, and we are going to multiply all those corresponding values together and then find the sum. So we're going to do the 0 times the 6, then we're going to add to it the negative 3 times the 3 minus x, and we're going to add to it the 1, right, times the negative 15 minus x, and we want that to equal 0. And so obviously that's already 0, so this is negative 9 plus 3x here. Okay, this is just distributing a positive 1, so that's easy. That's just minus 15 and minus x. Again, we want that to be 0. So combine like terms, negative 24 plus 2x equals 0. Add your 24, and we can see x equals 12. And that pretty much fits the bill, because if we went all the way over to 12, 5, right, we would have that point be collinear. And again, we could just confirm that with slope, and we could easily see that all those 3 points would be on the same line, but here's how we were able to do it using determinant values. All right, so I hope that you have learned a lot from our chapter on matrices. I hope that you've enjoyed it, and who knows, depending on what math class you take in the future, you might actually be thankful that you learned some of the stuff here this year. It depends, again, on what classes you take, but also there's quite a bit of questions on different matrices topics in the SAT 2, sometimes ACT and things like that. All right, hope everyone is well. Bye.